let's continue with the second method. The second method is designed to find the median of the set S, although we can easily change it to find the kth smallest element of the set S. So I will leave this for you as an exercise. Now the main idea for the second method is we are trying first to find two numbers. One of them, let's call it D, and the other is U, so that we hope that these two numbers are really close to the median of S. And we hope that one of the number, let's say D, is below the median, and the other number U is above the median. Now if we can have this D and U close enough to the median M, then we can make use of them to find the set of numbers in the set S that is between D and U. Now because D, U are really close to the median, the set S, after filtering by this D and U so that we get the set C, will be really small. So when C is small, then we can sort C by brute force, or actually not by brute force, by any reasonable n log n time algorithm. And after that, we can find the median M of the original set S. So this is the basic idea. So this is the input set S, and we hope to find two numbers, D and U. So let's call them GARs, okay? So these GARs hopefully will enclose the median M. So we hope that D is less than or equal to M, and U is greater than or equal to M. And then after that, we use DU to filter out those numbers which cannot be M. So we look at every number of S one by one, compare it with D, compare it with U. And if it is smaller than D, then it cannot be the median. If it is larger than U, then it cannot be the median. And hopefully, all the numbers between D and U, so we call this the set C, will contain the median. And finally, we sort C. We hope that C is small enough. And then we find the median M after the sorting of C. Okay, so how do we do these steps? So here in this method, we will rely on the power of sampling so that the following scenario will happen with high chance. First of all, by using sampling, we will get the number D, and then D will be below the median M. And then U will also be above the median M. And also, D and U are close to the median so that the set C will have small size. Now we are going to look at the details of each step. And after that, we will analyze the correctness, the running time, and also the chance of failure. So step 1 is to find D and U. So how do we do so? First of all, we are going to select a small portion of numbers from S. So S has n numbers, but we select much fewer numbers from S, n to the power 3 over 4. So it is really much smaller than the original set size n. And the selection carries here is done by uniformly picking a number from S with replacement. We call the resulting set R. So R contains n to the power 3 over 4 numbers, and possibly with repetition. So some numbers may be repeating. And next, we are going to sort R to find two numbers, such that these two numbers are having distance roughly square root n below and above the median of R, so that I'm using a different color here. So this is the median of R rather than the true median of S, okay? And then these two numbers, we set them as D and U respectively for our purpose. Okay, so let's see. So this is what we mean. So we have S, and we do sampling. So after the sampling, we have a small representation of S. So roughly speaking, because it is done by sampling, so R should look close to S somehow. And then we can, because R is now small, we can sort R. After sorting R, we arrange the numbers in sorted order, so we know clearly what is the median of R, and we look at the numbers with distance square root n away from this median. So one of them we call it D, and the other we call it U. Now notice that D is smaller than the median of R, and U is greater than the median of R, but there is no guarantee that D and U will be making the median of S in between. So this is not guaranteed. And then we want to bound the probability of having such a scenario. Okay, now how about step 2? Step 2 is simply the filtering step. So once we now have D and U, we can get the C, which is the numbers between D and U. Now once we have do this filtering, compare each item of S with D and U, we can really easily check whether the median of M is within C or not. If it is not within C, then we are failing. Or, alternatively, if the set C contains too many items, here we have a special parameter 4 times n to the power 3 over 4 to check, or we use it as a threshold to determine whether C is too large or okay. Now, if the median of S is not within C, or when C is too large, then these are two cases that we are unhappy. We will just abort the whole operation, and then we will say, oh, we fail. But otherwise, we are going to go to step 3. Okay, so what does step 3 do? Now, step 3 now finds the median M among the sorted C. So how do you do so? So first of all, after filtering, C is not sorted, so we are going to sort C. And in the filtering step, we can also know how many numbers of S are less than D. So we say that there are P numbers less than D, so we can get this as a byproduct of the previous step, so we do not need any extra operation. So after that, because our purpose is to find the n over 2 smallest item of S, but then there are P numbers that are excluded already from the set big C. So in that sense, we are going to find the n over 2 minus P smallest number of C instead. And this can be done easily once we have sorted C. It takes constant time once we have sorted C. Okay, now the running time. Okay, the running time for step 1, because step 1 takes only very few items from S as we sample, so the total number of comparisons is little o of n. Little o means that it is non-comparable to n. It is much smaller than n. And for step 2 is really the major part where the comparisons are made. We are comparing each number of S with D and U. And in the worst case, each number is compared with D and U at the same time. So there are 2 comparisons for each number, and in total there are 2 n comparisons. Now step 3 may not be performed because we may be failing already. But if it is performed, then it is guaranteed that the set big C will have a small size. So sorting this C takes only little o of n comparisons. So in total, no matter what happens, either we have all the 3 steps performed, or we just have step 1 and step 2, the total number of comparisons is at most 2n plus little o of n. And now, as we can see, as long as we do not fail in step 2, so as long as we proceed with all the steps, then we can find the true median of the big S. So what remains is we are going to analyze what is the probability of this algorithm failing. We want to show that this probability is really small. So in other words, the chance of this probability, the chance for this algorithm to report the median is high. Now we see that the algorithm will fail if the following occurs, and no other cases will make the algorithm fail. So first of all, the D value that we have chosen is greater than the median M. So this is a bad case for us. And similarly, the U that we have selected is smaller than the median. So this is another bad case. Now for the third case that we could be failing, it is when the size of C is really large, greater than 4n to the power 3 over 4. And the chance of failing will be equal to the probability of E1 union E2 union E3. So E1 occurs, or E2 occurs, or E3 occurs. And so this is less than or equal to the sum of the individual probability of these events. Why? So this is the union bound. Okay, so by union bound, we get this equation. Okay, now we are going to find out what is the probability of E1. And similarly, we can get the probability of E2. And finally, we can get the probability of E3. So we want to show that all these probabilities are small. So in that sense, the chance of failing is small. Now we want to bound P probability of E1 now. So first of all, let's examine when E1 occurs, what exactly will happen. So E1 is D is greater than the median. So if we look at R, D is supposed to be close to the median of R. But if D has a value greater than median, then what does that mean? It means that this R has so many items filled with value greater than m, and so few parts, so few portion is filled with values less than or equal to m. So on the expected sense, because R is a miniature of the big S, so we really expect that roughly half of this R will have value less than or equal to m, and roughly half of the R will have value greater than m, right? But in contrast, when E1 occurs, then only a few number of R has values smaller than or equal to m, and then it is really unlikely. So this is what we hope to show. So when E1 occurs, only a few of R will have value at most m, and then we want to show that this is really unlikely. So how do we do this? So let's define a random variable y to be the number of values in R with value at most m. Now before we see this final outcome, okay, when we perform the selection of the numbers to R, it is actually a process of picking numbers from the set S independently one by one. And then we will see that y, we want to find out the numbers in R, which is with value at most m, it is actually a binomial random variable with parameter n to the power 3 over 4 and 1/2. So we are having n to the power 3 over 4 draws. Each time we are picking a number that is in the with value at most m with probability 1 over 2. So actually, y is a binomial random variable, so that we know the expected value and we also know the variance. But now, when E1 occurs, then what exactly will happen is the actual R, the actual y here is much smaller than we expect. The actual y here is smaller than, this is half of it, and then minus this portion, which is guaranteed to be not smaller than or equal to m when D is so large. So in that case, this happens when E1 happens, then y has to be smaller than half of the numbers and then minus n to the power 1 over 2 minus square root n. So because we now know the expected value and also the variance, we can now change this probability bound into a term that we can apply the Chebyshev's inequality. So after changing it, so we find that this probability is less than or equal to 1 divided by n to the power some constant. So this is small. So we now have a bound for probability of E1, And also, similarly, we can have the same bound for probability of E2. And how about probability of E3? So let's take a look now. So suppose that the size of C is greater than 4n to the power 3 over 4. Now when this happens, what will be the consequence? So we will see that either one of the following or both will occur. So it may be more than 2n to the power 3 over 4 numbers of C will have value greater than m, or more than 2 times n to the power 3 over 4 numbers of C will have value less than m. So probability of E3, so when E3 occurs, A or B or both must occur. So probability of E3 is smaller than or equal to the probability of A union B. Because A occurs, B occurs is a consequence of E3 occurs. But then it is not always true that when A occurs and B occurs, then E3 must occur. So in that sense, probability of E3 is less than or equal to the probability of A union B, and by the union bound, it is further smaller than or equal to the probability of A plus the probability of B. So now we are going to bound probability of A, and similarly, we can bound the probability of B. So when will A occur? Okay, so we will see that A will occur. It means that in the sorted C, let's say the dark green portion represents the number with value greater than m. And then this dark green portion, when A occurs, then this dark green portion will contain at least 2 times n to the power 3 over 4 numbers. So the rank of this number U, so U will be, so the rank of an item is the number of items smaller than or equal to U. Okay, so here the rank of U will be much away from the middle median. So the rank of U will be at least n over 2 plus 2 times n to the power 3 over 4. So the rank of the median is n over 2. So in that case, there are at least 2 times n to the power 3 over 4 items here. So it makes the rank of U at least this large. So U will be a very large number in the original set S. But then, will this occur naturally? Now remember that how we select U. U was supposed to be close to the median. U was selected to be some number close to the median of R. So if U is such a large number in the whole set, that means that in the R that we have selected, we are selecting many large numbers rather than only a few large numbers that we expect as. So here, the red portion represents the number that are having rank larger than or equal to that of U. And then we will see that, not that of U, but larger than or equal to n over 2 plus 2 times n to the power 3 over 4. So these are very large rank number. And we need to have many large rank number so that U will also be then having a large rank. And then here, so intuitively, this is unlikely. So large rank number should only have a small portion rather than a large portion. So in that sense, we are going to do the same analysis as before. This time, we let's set to be the number of items in R. R is the random selection sampled set, such that the rank is at least n over 2 plus 2 times n to the power 3 over 4. So these are the large rank numbers. So large rank numbers is also a binomial random variable with the parameter n to the power 3 over 4 and the chance that we are having a large rank number selected in the set S. So this is the number here. And similarly, as before, we can, because it is now a binomial random variable, we know. so that we have the expected value, and then we have also the variance. Now we have these two so that we can find out what is the probability of A. Now probability of A means it is the case where there are so many numbers with large rank. So this is the case where we have so many large rank numbers inside the set R. And then using the expected value here and the variance terms here, then we can change this probability into a form that we can apply the Chebyshev's inequality. And after the application, we find that this is smaller than or equal to, again, 1 divided by n to the power some constant. So now this is in conclusion. So the probability that the algorithm is failing is less than or equal to probability of E1 plus probability of E2 plus probability of E3. And then each one of them, in turn, is less than or equal to 1 divided by n to the power some constant. So this is really, really small. So in that sense, the algorithm is correct or successfully runs until the end with high probability. That's the end.